Okay, so we finished our topics, and today this is what we are going to do. I'm going to solve the last tutorial questions. I think that's going to take about 20 minutes or so. Then I'll do something like an office hour, or I think what you call the consultation hour. I'll turn off the recording. So for those who are just following the recording, I won't be covering any new material, or I won't be covering exam questions. I won't be giving any hint for the exam questions or nothing like that. It's just that I'll respond to your questions. You can ask me to revise any topic or ask me any specific thing you didn't understand. You can ask me to solve some of the tutorial questions again, or point to where you didn't understand well so we can revise. Or in general, if you want to chat about something related to networks that you want to discuss about, we can also discuss those. So it will be more like a interactive environment. I'll turn off the sound recording, but I'm not sure about the video. I think our video may still be uploaded. You can ask questions from where you're sitting, or you can come here and point to me your specific question. All right. As you all know, exam is on the 4th of May, but please check that. Don't trust me. And as I mentioned in the last lecture, there will be a mix of questions, mostly problems, and some of them can be explanation questions, more short form answered, or explanation with a few sentences or so. It will be covering both parts, both the parts you covered with me and you covered with Professor Biplab Sikdar. Right? And I think I talked with Biplab. I think he'll be sharing with you the exam questions, the past year exam questions, obviously. Yeah. All right. Okay. So let's solve the last tutorial. So here we have the authentication protocol from class. This is for endpoint authentication. Alice is proving Bob that she is indeed Alice and that she is live on the other end of the communication. So Alice authenticates herself to Bob. Which we saw works well. So this is using symmetric key cryptography. So Alice is saying to Bob, I am Alice, and then Bob is sending her a nonce. We learned that this nonce is a one-time pseudo-random value that is not supposed to be repeated in the lifetime of a communication. And then Alice encrypts that random nonce with the symmetric key that only Alice and Bob knows, but no one else. And this way, because Bob knows that this key is not possessed by anyone else, so no one could have obtained KAB of R, so that Bob knows this is Alice on the other side. So now let's look at the question. Suppose that while Alice is authenticating herself to Bob, Bob must authenticate himself to Alice. Give a scenario by which Trudy, pretending to be Alice, can now authenticate herself to Bob as Alice. So let's draw these here. Let's say this is Trudy and this is Bob. In my first scenario, Trudy will be authenticating herself to Bob, and simultaneously Bob will be authenticating himself to Trudy. So what is the first thing Trudy says? She says, I am Alice, right? Because she's impersonating Alice. And what will Bob say to Trudy? He will say, obviously, I am Bob. And now, after Trudy tells Bob, I am Bob, what does the protocol require? It requires Bob to send a nonce, correct? So Bob will send Trudy a nonce value. So this will be a different nonce value. So let's denote this by R prime. It has to be different than the previous nonce value Bob used, for instance. And now, if Trudy successfully wants to authenticate herself to Bob, what she can do is she can simply use the same nonce value that Bob sent her, R prime. And Trudy, on the left side, when authenticating herself to Bob, she is just going to wait until Bob tells her the encrypted version of R prime. In other words, R prime encrypted with the shared symmetric key of Alice and Bob. So now, Trudy doesn't have to know KAB. She doesn't have to know what KAB is or how to encrypt R prime to get this KAB of R prime. All that matters is that she obtains this KAB of R prime, and she can simply respond to Bob with that KAB of R prime. So this works. So that means this protocol can work only if we allow Bob to authenticate, if we allow someone to authenticate herself to Bob, but if we allow both parties to authenticate simultaneously to themselves, they can use the same nonce value, and this authentication will not work. In other words, anyone, any attacker, can authenticate themselves as Alice or anyone that Bob shares a symmetric key with. So, any questions here? Then one question arises then, how can we prevent this kind of attack? It's not in the question here, but let's think about it. So how can we prevent this attack from happening? Well, for one thing, we can have Bob to keep a record of all the nonce values that he sent, so that when he's sending challenges, if the challenge he sent is the same as the challenge he received, that won't be accepted as a proper authentication method. This is one method, but it doesn't make much of sense, because then Bob needs to put everything in the storage, all the past nonce values in the storage, so that no one requests that same challenge from Bob. A better approach could be to use public key cryptography here. So instead of, let's say this protocol here, instead of, say, sending or requesting KAB of R, we can change the protocol so that the authenticating party, Alice in this case, authenticates herself by encrypting the nonce or the challenge with the private key. But this, of course, requires Bob to know the public key of Alice. This can be obtained by a certificate authority, or this can be asked to Alice, and Alice can send her own public key, which is certified by the certificate authority sometime before. So both ways are possible. So this is a better approach of preventing that kind of attack. Because if we do this, then even if Trudy in our scenario uses the same nonce value here, let's use another color there. Okay. Let's say our Trudy here requests the same nonce. What Bob will send her will be, instead, KB minus of R. And what Bob will expect from Trudy will be Ka minus of R, which Trudy did not obtain in this scenario. Correct? Trudy did not obtain Ka minus of R. So this works. Any questions? Okay. So let's look at the second problem. So now we are considering a scenario where Trudy is sitting on the communication channel between Alice and Bob. So when we say sitting on the communication channel, we can say that Trudy can just drop messages, she can tamper with messages, she can forge new messages, compromising both the confidentiality and integrity and authenticity of messages. So Alice uses the following protocol to send a sequence of messages M1 to Mn to Bob. So all these messages, and then she sends all the hashes of the message concatenated with a key. So what is that key? K is a symmetric key shared between Alice and Bob. In other words, these are the message authentication codes, right? What we learned in the class. So these provides the evidence of the authenticity and the integrity of the messages. If that shared key is shared between Bob and Alice only. And H is a cryptographic hash function that is known to everyone. So Bob wants to ensure that the messages were first indeed sent by Alice, and that they were sent by Alice in the order in which he received them. So two things. And we are going to look at if this protocol guarantees these two things, or just one of them, or neither of them. So we know that regardless of when you send the message or when you send the MAC, you can send them together, you can send the MAC later on. But this hash, this message authentication code from M1 could only be obtained if you possess K, because we know that hash function is a one-way function, meaning that you cannot compute the message from its digest. You can only go one way from the message and the key to the digest, right? This is a property of the hash function. It's pre-image resistant. So it provides this first property. It is indeed, all these messages are indeed sent by Alice. In other words, this is the very basic message authentication code, right? In authenticating a message, we send the message plus the message authentication code computed with the shared key. So Alice did this for all the messages from M1 to Mn. And let's look at the second one. They were sent by Alice in the order in which he received them. So if Trudy is now sitting on the communication channel between them, what she can do is she can just block all these messages. In other words, she can just take them and block them. Now she has all the messages from M1 to Mn. And then she can replay them to Bob in any order she wishes. She can replay, for instance, M2, M1, M3, and all the way to Mn, or any order, any arbitrary order that she wishes. And then she can do the same with the HMACs, the message authentication codes, the MACs. She can, for instance, she can send this one first, this one second, the third one in the third sequence, and the rest in the correct order, or any sequence that she wishes. If she does this, then Bob has no way of knowing which message is the first message. So this protocol does not guarantee the order of the messages. So now the second question is, if any of these properties are not satisfied, how can we change the protocol to provide these guarantees? So message integrity and authentication guarantee is satisfied. So the messages are indeed sent by Alice. But how can we guarantee the order? Well, for one thing, we can have Alice add a sequence number in each of these MACs. For instance, she can tell, we can structure the protocol in a way that in the hash, we take three things. We take the K, we take the message, and we take the message's order. For instance, now she will send h of k m1, 1, and then she will send h of k m2, 2, and so on. Or alternatively, we can just put a timestamp instead of these sequence numbers. So instead of this 1, we can put in the exact time here. And because these time values will be ordered according to the time these messages are generated, Bob can still put them in the correct order. Even if he receives the max or the messages in a different order, he can arrange them in the correct order. And Trudy, not knowing this k value, she cannot create this message authentication code because of the pre-image resistance of the of the hash function. All right? Questions? Okay. Then that's all for today's class. Now I'll have your questions.